Hello everyone, and welcome to part 3, which is also going to be the last part of the 3.4 notes, where we're discussing the zeros of polynomials. We've just seen how to find zeros by using synthetic division and by being able to basically make an educated guess about which kind of rational zeros you should try in that process. What we have here is just a list of some theorems that exist that basically correspond to this idea what we're talking about. They have a lot to do with polynomials. They have to do with also the zeros of polynomials, and so we just have a list of them here. We can take a look at them just so you know them. There's this one. It sounds so important, the fundamental theorem of algebra. And what this one says is that if you have a polynomial that is at least degree 1, and so in other words it has to at least be linear. It cannot be, for example, this one, a constant polynomial like f of x equals 1. This would have degree 0. And so this one, it has to have at least degree 1, so it has to at least be like a y equals mx plus b, give you a line, for example. And it has complex coefficients, which complex numbers also include real numbers, because complex numbers are these kinds of numbers, which actually later down the page we define what they look like, but they're numbers that go a plus bi, where a and b both have to be real numbers. So if you just choose, for example, to make b be 0, then you just are left with a number like a. And so if you just have a by itself, it's still a complex number because you could write it this way, but just making b be 0. But any kind of a polynomial that has these kinds of coefficients, we know for sure based on the fundamental theorem of algebra that it will have at least one complex 0. So it would be possible to identify a 0 for that polynomial. And it's actually this last one that we have right here. This last kind of it's not listed as a theorem, but it is having to do with the number of zeros. This is actually an equivalent statement to the fundamental theorem of algebra. Sometimes the fundamental theorem of algebra actually will be given this definition, the way that this one is stated here, that if you have a polynomial with a degree of n, and it has complex coefficients, so it counts also real coefficients, then for sure that function, that polynomial function, will have the same number of complex zeros as the degree. So we would know, for example, if f of x, if this is a cubic, like x cubed with some stuff, it's a cubic function, because the degree is 3, we know that there will be 3 complex zeros for this function. There cannot be less, there cannot be more. There will be exactly that many, and sometimes this is called the fundamental theorem of algebra. But then we have something that comes right away from the fundamental theorem of algebra. It could be called a corollary, for example, because it's so much related to that one. It's the fact that we can factor every polynomial in the world. We can factor it into linear factors like this, where each factor corresponds to a 0. So this task that we've been doing before of using the synthetic division to try to find factors, which is the same thing as trying to find zeros, what we know for sure is that if you do it all the way to its conclusion, and you include looking for every kind of every complex number, so you should be looking for solutions that have I in them as well, then we will be able to factor the polynomial all the way. We don't have to say like plus something at the end. We can just factor it into linear factors this way. And there's this other idea which is very important. We're about to use this one, this idea of conjugate zeros. This term conjugate, it comes up in a lot of different kinds of contexts inside of mathematics. We call different things conjugates, but it's always the same general idea. The conjugate of something, like here we're talking about the conjugate of complex numbers. If you take a complex number like this, a plus bi, its conjugate will be a minus bi. And the point of this theorem is that if you have a complex root of this form that actually has an imaginary component, then its conjugate will also be a 0. So these kind of, it's also what this one is saying is that these kind of complex roots that have an imaginary component with an imaginary component, they will always come in pairs with the conjugate. So 1 and its conjugate, they will always be in pairs. And so, for example, this number 4 right here, taking a look at number 4, this example, tells us that 1 plus 5i is a 0 for this. Then we're supposed to find the remaining zeros, and we should also end up factoring this thing as linear factors. Now, this is a complex number that has a non-zero imaginary part, and so we know that based on the conjugate zeros theorem, 1 plus 5i, which is the conjugate of this thing, this has to also be, is also a 0. And so we'll be able to use that fact. And so we can carry on with this problem in a few different ways. Something that looks very tempting to me is just to try to divide this one. We already actually know what 2 of the zeros are, and if you pay attention to the degree of this polynomial, it's a degree of 3. And so there is actually only 3 zeros for this, and we already found 2 of them. We just need to find the other 0. And so what if we try to do this synthetic division by picking a rational 0 that has a factor of negative 26 divided by a factor of 1. So actually, there's nothing to choose from there. You will see, based on the previous videos and how we choose these ones, that actually we could choose 1. You can see if this will work. And then I'm just going to put the coefficients down here. None of them are missing, so we don't have anything to worry about there. And then we would just carry on with this synthetic division, bring down the 1. 1 times 1 is 1. We add these up, get negative 2. Go times 1, get negative 2 again. And then add these up, it's 26. And then whenever we multiply these, 1 times 26, it becomes 26. And then when we add them, negative 26 plus 26, it becomes 0. So I'm relieved that it worked. Of course, it's possible sometimes to just look and see if 1 will work, because cubing and squaring 1 is so easy, so why not just try it? But anyways, we have found the other 0 is 1. And so the zeros here, they are 1, and then 1 plus 5i, and also 1 minus 5i. And so if we want to write it as a product of linear factors, this function f of x, we would write it as x, and then we just need to write them basically as x minus the factor, like x, or rather I should say x minus the 0. So x minus 1. Also x minus this thing, 1 plus 5. So 1 plus 5i will become minus 1 minus 5i. Because basically I subtracted like x minus 1 plus 5i. And then just distribute the minus, you get this one. And then kind of the same deal here. We're going to do x minus this thing. And so we'll go minus 1 and then plus 5. So x minus 1 plus 5i. This is that function as a product of linear factors. And that does it for us. We see how to apply these theorems. It can be useful, especially this one about, the conjugate zeros theorem. It's useful. This other problem, I will leave it for you to practice. That you're given a solution, which is very nice to have that solution given to you there. You want to find the remaining solutions basically by going through this process of repeated synthetic division. Of course, whenever you find a factor, you don't want to go back to the original polynomial. You keep going with the one that you found in that step. But anyways, I hope this was helpful. And if you have any questions, don't hesitate to ask. I'll see you guys in the videos for 3.5. Thanks.